E aí, mulheres? Tudo certo. Ai, cadê minha garrafinha? Eu vi sua garrafinha agora, cadê a minha? Eu tive a impressão que eu vim com ela na mão, mas eu acho que eu não vi. Pra mim tem que ser que não vaza também, porque eu soco na mochila e é isso. Ah, é bem bom também, que cabe bastante. Uhum. Sim, é claro. Tipo assim, a garrafinha de plástico só tem que ter cuidado pra não ser aquela molenga. Aquela molenga é o ó, mas a quando é durinha.
Olá, tudo bem? Bom dia.
Calma, Lina. Eu acho que é. Tá bom, acho que é. Porque uma moça que ela fez outra coisa da Erich. Aí ela vai ter que fazer a prova. Desenvolvimento de pesquisa, entendeu? Começou para a gravação daqui. É porque tem um momento que todo mundo sai da sala e só a banca fica para conversar e definir a nota. Nossa, deixar mais. Beleza.
Então, né, no YouTube, tá? Tá dando vídeo disponível, a Sara me mandou.
Mas voltando não no vídeo, talvez?
Tá. Manda o link no grupo pra eu mandar pra Sara.
José Alfredo primeiro all of you are going to and the last part we have to say if he is able to have PhD or not. So we have a try creativity at the end. These participants are is live on YouTube. So, Suzanne, so maybe you can start.
Just going to share my screen.
falar com ela assim, eu tenho que clicar, né? Aí.
E obrigada, pessoal, por estarem aqui, tá? Que não vai ter um pouco atrapalhado.
Não sei. Agora eu ia se apresentar.
Sorry, I'm missing myself. Just a minute. Okay. So, the thesis is entitled as Advances in Understanding the Influence of Clinker Chemistry and Mineralogy on the Performance of Portland Cement. So, this we all the great environmental impact that the cement industry has. We are talking about 6 to 8% of all the anthropogenic CO2 emissions. So the main goal of the cement industry nowadays is to drastically reduce CO2 emissions to reach the so-called net zero by 2050. And to do this, to achieve this, the industry needs to adopt several different strategies. Among these strategies, a very promising one is the use of alternative fuels. The idea here is to replace very intense CO2 emissions fuels like petroleum coke with other that emit less CO2. For instance, some industrial waste in the practice called co-processing. But by doing this, by changing the fuel, we also change the clinker. Why? Because there is the incorporation of the ashes of the fuel into the melt. So we are incorporating different types of minor elements. And this, yet we don't know how these elements affect clinker mineralogy and therefore how impact cement performance. So we are going to a future that we use different types of fuels, but yet we don't fully understand how each element can impact the cement performance. Another straightforward strategy is to reduce the clean factor through the use of supplementary cementitious materials. So we want to reduce the clinker, that is the fraction that most emit CO2, by using calcine clays, slags, fly ash, and limestone filler. Every time more SCM and less clinker. So we are achieving reduced clinker contents. We are talking about something like 30%, 35% of clinker. So I ask you, does the clinker need to remain the same? One cement with 30% of clinker needs to have the same clinker of ordinary Portland cement with 95% of clinker. Can we optimize this clinker for these blended cements? And one of the main market limitations of these new types of cements are the low early strength. We are talking about the strength at 12, 14 hours to 1 day. And a lot of research is going on nowadays to optimize the supplementary cementitious materials. This is very valid, but this first day of reaction is mainly controlled by the clinker fracture. So a key strategy can be to optimize and increase clinker reactive to increase early strength. So towards the cement of the future, we need first to fully understand the impact of minor elements that can come from these alternative fuels and see how we can enhance clinker reactive without increasing CO2 emissions. A lot of research was going on and developing in the 80s and 90s, but for the last 20 years, we lose some of studies on Clinker, but yet a lot of knowledge gaps persist. So we need to return to these studies to fully understand these impacts on Clinker. With this in mind, the goal of my research was to investigate the influence of Clinker chemical composition on its mineralogy and explore the consequential impact on cement products. As a specific object, we have to characterize and evaluate chemical, mineralogical, physical variability of industry fossil clinkers from different cement plants in Brazil, identify key composition parameters that govern breathability, hydration kinetics, and strain development. Also, to investigate how the chemical composition of Portland clinker influences the formation, distribution, and polymorphism of its mineralogical phases. We also have assessed the accuracy and limitations of conventional and advanced X-ray diffraction techniques for the quantitative phase analysis of clinker, investigate the effects of clinker chemical composition and mineralogy on crucial aspects such as sulfate demand, hydration kinetics, mechanical performance of cement, and finally assess the feasibility and efficacy of employing mixed design experiments to optimize clinker compositions. This study was structured in 4 different studies. Each of them is a paper. The first 2 was published in Cement Concrete Research in the beginning of this year, while the other 2 are not submitted yet, are in preparation. So the first article is entitled as Revealing the Key Factors for Clinker Reactive and Cement Performance, a Physical, Chemical, and Performance Investigation of 40 industrial clinkers. In this study, we sampled 40 clinkers from 16 different cement plants in Brazil. It's important to say here that all this methodological experiment was developed by a cement company, partner of this research, and provide us the data and we analyze the data. So they collect these clinkers and then characterized by XRD, XRF, and optical microscopy. Then grinded in a ball mill for 1 hour. So all clinkers were grinded in the same time in the same grinded setup. The idea here, obviously, we will obtain clinkers with different particle size distributions that will affect the activity. But the idea here was to evaluate how the grindability, how hard it is to grind the clinker will affect its properties. Because a clinker harder to grind means more energy and more resources to grind. So all the clinkers were grinded by the same mill and tie. We didn't optimize the sulfate content here. We used 95% of clinker per 5% of gypsum, doing time in materials limitation restriction. Then run isothermal up to 7 days and compressive strain at 1, 3, 7, and 28 days. Here are the results. These results, first of all, is very interesting because it's a picture of the clinker in Brazil. Obviously, it's from one company, but talking with other cement partners in Brazil, this is a very good picture of the Brazilian clinker. So we have here the main chemical compositions, but I highlight here the other. We have clinkers varying the magnesium content from 1.9 to 7.5%, a very high content. And here we have this in Brazil. In the south of Brazil, the limestone has a great content of magnesium, while in the northeast, we don't have a lot of magnesium. We also have a very great variation of sulfate from 0.5 to 3% of sulfate in clinker, not in the cement. So a very great variation due to the variation of the tube used, and also alkali vary a lot. And here we have that I highlight the fossil, that we had some clinker to 0.7%, and the titanium to almost 0.8%, due to raw material impurities or due to co-processing. And here we have the mineralogical of this clinker, mineralogical composition, and we have a variation of a light between 56% to 73%, the light between 4 to 24.5%, C3A between 2.3 and 7.7, and C4AF from 7.4 to 13.1% of the clinker. So we have a great variation on clinker mineralogy as well. Here is the allied average crystal size that also varies a lot, obtained by optical microscopy. And here we see a variation from 20 micrometers to 60 micrometers. According to the textbook of Taylor, good light crystal size would be below 25 micrometers. Here we have the results of heat relief and compressive strength. We also see a great variation among the clinkers. And now we compare all of these results, trying to see relationship between the variables to try to explain the results. So here we use Pearson's correlation, so indicates if a variable correlates linearly or not with a property. So here we see total allied and total delight content. Obviously, if something is influencing positive the allied, is decreasing the delight. So this was as expected. Here I highlight the limestone saturation factor. As expected, the higher the limestone saturation factor, the higher the allied and the lower the delight. But here I have this sulfate magnesium rate. The influence was higher than the limestone saturation factor itself. If we have more sulfate, the sulfate will stabilize the light instead of allied. While if we have magnesium, magnesium will promote allied instead of the light. So here we see the influence of minor elements instead of the 4-1, the 4 main one. Magnesium and sulfate has a great impact on allied and daylight content. And here we see clearly that we see sulfate, daylight, white, allied. This is also according to the literature. Here in C3A and C4AF, for C4AF, as expected, the main influence was of the ion, but we all take some sulfate again and alkalides. If we increase sulfate, we will form more C4AF and less C3A. While increasing alkalides, we increase C3A and decrease C4AF. Here is also interesting to see the magnesium grow again. It is very influential, and the higher magnesium, the lower the C4AF. This is interesting. We saw some compatibility results in the literature, but after with some partner, they observed somewhat different. The magnesium stabilizing C4AF. So we need to progress on this type of study, the role of magnesium on the alumni dates. Here we see about the polymorphism, and the polymorphism of C3S was, according to the literature, increasing sulfate stabilize C3S in 1, while increasing magnesium stabilize C3S in 3. And regarding the C3A polymorphism, the main influence was the sulfur alkali rate, sulfate alkali rate. And we see clearly from this graphic, above 1 sulfate alkali ratio, we almost only have cubic C3A. More than 80% of the C3A present in the clinker is cubic, while below 1 it's a linear correlation between the percentage of orthorhombic citrate and the citrate ratio. This agrees well with the practical experience of the cement industry. Now, regarding the distribution of sulfate, this will be important in the third study. So I highlight here that not all, here is the total sulfate content in Clinker, while here is the sulfate present in alkali sulfates. And we can see that there is a discrepancy, meaning that not all of the sulfate that we have in Clinker is present as alkali sulfates. If you look better to this, we see that increasing the sulfate alkali ratio decrease the percentage of the sulfate present as alkali sulfate. This meaning that if we don't have alkali enough to react with the sulfate, the excess of the sulfate that don't volatilize in the new will be incorporated in the main clinker phases, especially alide and mainly belite. And also we see something like this. We see that up to 1.7 to 2% of magnesium is incorporated in the main cement phases, while the excess will form very clays with a very strong linear correlation. As in terms of reactivity, here's the main influence on the heat release. We see, as expected, that the main influence was the sodium, the potassium oxide, the alkali. The greater the alkali content, the greater the clinker reactive at 1 in 7 days. And in terms of physical, we always see the influence of phosphorus. Phosphorus is a known retarder of cement reaction, but here we see that a strong influence 1 day at 1 day, but not at 7 days. That is according to the literature as well. And in terms of physical and mineralogical aspects, we see obviously the finer the cement, the greater the reactive is. But we also see here the influence of allied crystal sizes. The larger the crystals of allied, the lower the reactivity of clinker. This is somewhat discussed from the 80s and 90s studies, but somewhat was forgotten in the last year. In terms of compressive strength at 1 day, we see here that the most influence was again sodium and potassium oxide, positive at 1 day and negative at 28 days, as also observed in the literature. We also saw an influence of manganese oxide that we could not explain. Perhaps there's a correlation with sodium, potassium, or other thing that we couldn't see, but it's something interesting to investigate. And here we see the influence again of the fineness of the cement. The finer the cement, the higher the compressive strength at 1 day, and also the influence of allied crystal size, converging with the heat evolution result. So here, the allied crystal size was more important than, for instance, total C3F or total C3A content. So meaning that it's not only the bulk composition of clinker, of the main oxide, C3F, C2S, C3A, C4AF, that matters for reactive. And again, we see a good correlation between total heat and compressive strength, particularly at 1 day, according to the literature as well, but not good and strong at 3 and 7 days. Obviously, talking about different clinkers and different cements. So if we got only one clinker, we will see a good correlation between strength and total heat, because the total heat is a measurement of degree of hydration. But when comparing different clinkers with different composition and mineralogy, we don't see this correlation. So we see here the conclusions that the average composition of clinker Brazilian clinker was 67% of alite, 12% of belite, 4.3% of C3A, and 11.1% of C4AF. Alite was monoclinic M1 or M3, but mostly M3. Belite was the beta polymorph. C3A, most clinker has both cubic and orthorhombic, but the main polymorph was cubic. We saw the influence of sulfate magnesium ratio on the silicate. When we increase sulfate, we decrease alite and stabilize more belite. And increasing sulfate, we also stabilize alite M1. While magnesium stabilizes more C3S, C3S M3. We also see the influence of sulfate alkaline. When increasing sulfate, we decrease C3A and form more C4AF. And this ratio basically controls C3A polymorphism. In terms of reactive, the potassium oxide had a positive influence at 1 day, both for hydration and strength. And the phosphorus oxide negative. The final descendant, the faster. Because long term, 28 days, the alkali was negative, as also previously observed in several different steps. So now going to the second study, that is entitled polymorph phase quantification in Portland by X-ray powder diffraction, addressing challenging and far-reaching effects. Here we contain 8 different clinkers, not the ones used in the previous study. So these are new clinkers, different clinkers. 7 gray ones and 1 white Portland clinker from Colombia. And we analyzed by XRF, scanning electron microscopy and optical microscopy, and also by XRD. Lab XRD is with and without movement, and also synchrotron XRD. Here we see the chemical composition of the clinkers. I highlight first that the white Portland clinker has a low amount of impurities, as expected, so a low amount of amino elements. I highlight also the great variation in magnesium, sulfate, and alkali content. And finally, I highlight that the PCB has a amount of minor elements, because this plant comes from uses a limestone with low purity and a lot of coal processing. Here I highlight also the great variation in a light crystal size from 21 to 74 micrometers. And also here we use a different strategy from the first study. Here we vary the time of grinding to obtain particle size distribution. Here's the scanning electron microscopy results. And I highlight here the composition that both alite and belite incorporate minor elements. And here I highlight that belite incorporates a lot of sulfate. Here are the results comparing the quantitative phase analysis among the 3 XRD setups that we have here. So here we see a significant influence on the XRD stars on the alite and belite quantity. Here, the synchrotron XRD led to higher C3S content with difference up to 5.7%, so very significant, while the lab XRD without monochromator led to higher belite content with difference up to 6.7%. And this graphic here may explain why there's a great effect on XRD source on the belite and alite composition. In terms of the aluminate C3A and C4AF, the influence was not significant. All the ones presented similar quantities among all the setups used. In terms of polymorphism, we also see a difference for the XRD that we were using. the single XRD led to C3SM3, while the lab XRD, especially the one without that is led to C3SM1. In terms of C3A polymorphism, we only observed C3 in the first 3 clinkers. The others was 100% cubic, but we also see a great difference in this. And we also run here some analysis selective dissolution process to remove all the silicates and help us to properly identify and quantify the C3A fraction. And here I have that the most different from the selective dissolution and the other was again the lab XRD without monochromate. So also talking about the result, we see here a great combination of allied with sulfate and magnesium, again, as observed in the first study. The higher the sulfate, the lowest the allied content, and the highest the belite content, while the magnesium stabilized allied instead of belite. Again, agree with the first study. But here we also follow an significant effect of alkaline. The greater the alkali, more allied is formed. This might be due to the reactions between sulfate and alkali. If we have alkali enough, the sulfate will react with the alkali to form alkaline sulfate. If you don't have alkali enough, the Sx of sulfate will enter into the silicate structures, stabilizing more belite and less allied. And it's very interesting to see this and compare to this result. We see that what stabilizes allied, the total allied content, is the opposite what to stabilize C3FM1. So to stabilize C3FM1, the sulfate is good, while the magnesium and alkali stabilize C3FM3. This is also agreed with the results of the previous study. In terms of C3A polymorphism, we also observe a great influence of sulfate-alkali ratio. Yeah, but here we saw an exception, PCB. We evaluated 40 clinkers in the previous study, but here PCB was an exception that had a very high sulfate-alkali ratio, but it also has a great amount of orthorhombic C3A. This may be coming from the mineral, as I said before. PCB is a plant with a lot of impurities, so perhaps phosphorus, titanium is stabilizing the orthorhombic fraction of C3A. So, as conclusion, we saw a great influence of the XRD setup or source, while single-drone XRD led to higher allied and lower belite, higher C3S and 3. The lab XRD, especially without the trend. Obviously, I'm not saying to always use single-drone XRD, but just to understand that matters, that influence the result. And on Clinker chemical composition, saw that again, sulfate magnesium ratio and alkalis was very important to C3S content and our C3S polymorphism. Sulfate stabilized more belite instead of allied, but stabilized C3S1, while magnesium and alkalis stabilized more C3S and more C3S3. We also see again the great influence of sulfate alkali ratio on C3A polymorphism, but an exception that was PCB that also had orthorhombic despite having sulfate alkali ratio very above 1. So going to the third study, here we evaluated the Clinker composition mineralogy role in determining sulfate demand in cement phases. So here we use the same clinkers from the previous study. We guided, as I said, to obtain similar particle size distributions. So we vary the type. And here we optimize sulfate, varying the gypsum, varying the sulfate content, and optimize the sulfate with isothermal calorimetry. We then analyze the phase assemblage in the first 24 hours by C2XRD, and here we run only the optimal mixes, optimized mixes, but also two others that I will show after. So just to explain how we can optimize sulfates, there is a again, C1C50 that explain this method. We can do in different ways using strain, but in terms of calorimetry, we can analyze the heat flow curve, and we want to see that the shoulder peak is a few hours after the main syndicate peak, or we can plot the different total heat at 24, 48, 72 hours, and see the one that will release more heat. The one that releases more heat is the optimal traffic, optimal content. But there is other ways. For instance, the one scripted that we plot the heat release until the illuminate peak onset, meaning until the sulfate deflation point, against the total asphalt train content, and we do a regression, and we analyze the interception, and also the slope of this regression, meaning if the means more or less sulfate. I will explain again later this difference. So in the first Clinker, here we see first with the lowest level of sulfate, 2%, we see clearly an undersulfated mix. Yeah, because we don't see the shoulder peak. When we add more sulfate, 2.5%, we see a variation in the main silicate peak, but we also don't see the shoulder peak. When we reach to 3%, we now see the shoulder peak. So we are reaching the opposite. Then we go to the 3.5%, and we see this shoulder peak in a few hours. So I would say that the optimal content would be something between 3 and 3.5. Because when we go to 4%, we see the shoulder peak here. It's very late. And when we see 4.5% is here. So if we analyze the total heat now, we can see that indeed the optimal content will be between 3 and 3.5. In this case, 3.23%. And we did this for the 8 Clinker. So PCE, according to heat, will be between 4 and 4.5, and according to the total heat, 4.25%. For PCC would be between 3 and 3.5, and total heat 3.23%. BCD between 3 and 3.5, and for total heat it's like outside the range, but to 2.98%. For PCE between 3.5 and 4%, the total heat 3.69%. PCF again 3.15%, and PCG a very high sulfate number 4.34%. It's important to highlight here that this optimum is more a range than a point itself. With this method, we get a optimum content, but it's more a range. So here between 4 and 4.5 than a point itself. And everything goes as planned, went as planned here, until we arrive at the white Portland Clinker. Here things become weird. So the white Portland Clinker almost doesn't have sulfate, only 0.13%. So I added only 1% of sulfate to C, and there you have this behavior. This behavior is very clearly of a very undersulfated mix. Behavior very similar to pure phase cement, C3A and C3S systems, that we saw a very sharp peak here at the beginning, that is from C3A reaction, and later this one that is from C3S hydration. And we also confirm this by C2XRD, as I will show later. Then we add more sulfate, And here, they lay this peak until after the main silicate peak, and here we see the behavior that we was expected. This peak comes occurs early. And see here we observe the influence of the undersuppated on the C3F reaction. Then we have more, and we have the optimum zone. So according to the heat flow, the optimum content would be something between 2 and 2.5%. If we add more sulfate, this shoulder peak becomes very late, meaning oversulfated. So we added 3.5, we added 4%, and 4.5%. But I also highlight here that the white Portland needed released a lot of heat in this aluminate peak compared to the gray Portland Clinker, but besides that, it needed a low amount of sulfate. 2.5% was enough to optimize, while the gray ones needed more than 3% of sulfate. And if you go to the total heat, the optimum zone would be 0.98, and it's really not sulfated. This means that the total heat method cannot be adequate to the white Portland Clinker, and we saw some similar behaviors like this in some LC3 calorimetric curves with a high aluminate peak. So perhaps in this sense, white and LC3 is better to optimize with the heat flow than the total heat. And here I compare PCE and white concrete cement Clinker. And this was very interesting. We were lucky because PCE has the same content of C3A with white concrete Clinker. So why the concrete have the peak? You could say, oh, perhaps the C3A content, PCE has the same content. Or could be C3A polymorphism. Both are on theory, as shown here. In fact, PCE has a slight higher C3A content. So it's neither the C3A content or the C3A polymorphism that can explain this higher aluminate peak. So our hypothesis that need further investigation to be confirmed is the absence of iron, the absence of C4AF. Here is a scanning electron microscopy from PCE. We see here the behavior that we expected, very intermixed C3A and C4AF between light and white crystals. While in the white Portland cement, we don't have C3A, so this interface is only we don't have I, so the interface is only C3A. So what is happening here, our hypothesis, is that in the gray Portland Clinker, the C3A surface is partially blocked by C4AF. So here in the white Portland Clinker, you have more surface for the C3A to react while adding water, which can explain the highest C3A peak on the calorimetry, and what explains because when we use systems of C3A and C3A and C3F, we also see this higher aluminate peak. And also that this interface here are worse than the gray Portland, which can also explain this. So here we have all the calorimetric curves at content or at the same as SO3 content, 4%. We see the great difference between the clinkers, where the induction period, the silicate peak, and here I highlight PCG that has the highest silicate peak. We couldn't find an explanation in the mineralogical composition of this clinker. Perhaps is due to uncontrolled factors such as quenching and that can promote different effects on allied crystals and increasing allied reactivity. So due to process parameters that we didn't control here in this research. And we run an in situ XRD analysis in all of the optimized mixes. Due to the time, I will not show everyone of them, but here we see the similar behavior. Yes, constantly up to the end of the period when we start to dissolve and form CSH in Portland dye. And in terms of aluminate, our initial solution of C3A, then C3A keeps the same for the first 24 hours, while it's forming entering dye, dissolving gypsum, until the minute that not enough gypsum is in the system, and we start from AFM phases. So we saw this for all the optimized mixers, agree with the calorimeter data with the quantitative phase analysis. But here we have a different idea, and we ask ourselves, the sulfate that is in clinker is controlling aluminate reaction or not? Or it's only the sulfate coming from calcium and sulfate gypsum. So we run the analysis without sulfate in the clinker. And here we see clearly from this, all of these mixes are severe undersulfated. But here we see in this that the sulfates are taking part, because we have here a peak aluminate peak here, 4 or 5 hours after the beginning of the hydration. So the sulfate in clinker is participating in the reaction. If you don't believe me, I run XRD analysis, and we saw here. Indeed, it's forming ethylene when we don't have gypsum. So ethylene is using the sulfate coming from the clinker. So the sulfate in clinker indeed participated in the aluminate sulfate reaction. Here, 1.5, and here we see different. Here we see that this peak is indeed without the silicate begins after. But something very interesting is that we got a maximum ethylene content. Then we can calculate how much sulfate would be expected. 1.7, 27, 26% of sulfate. So not all of the sulfate is going to ethylene. So perhaps not all of the sulfate is soluble, because we have sulfate in B light and in a light, as shown in the previous study. We also see here in terms of white cement clinker with 1 and 2.5% of sulfate. So, what explains the different optimum sulfates from the clinkers, varying to 2.5 up to 4.3%? We try to analyze Pearson's correlation with every parameter that we could find, so chemical and physical and mineralogical. And we don't see good correlation, for instance, from the alumina content in clinker, or from the C3A content in clinker, or the C3S content in clinker. Obviously, I'm not saying that aluminum, C3A, and C3S contents doesn't influence optimal sulfate content. Indeed, influence a lot. But what I am saying here is that these parameters alone are not enough to define the optimal sulfate content. So I cannot predict the optimal sulfate content of a clinker basically only with C3A, C3S, and aluminum. But what we saw here that was very interesting is that the most influential one was the sulfate coming from the clinker. And it's a very strong positive correlation. So if we got here, PCG is the exception, but we see a very strong linear correlation between the optimum total sulfate content and the clinker. What this is meaning? It's meaning that if I have more sulfate in the clinker, the optimum total sulfate will be higher. So it doesn't make a lot of sense at the first, but what this is meaning to us is that not all of the sulfate in clinker are participating into the reactions to control aluminate reaction. So this is meaning that we cannot take all of the sulfate into account to optimize. We need to consider only the soluble sulfate at the first 12 hours. That will be the sulfate that indeed participate in control C3 hydration. So, and obviously, this again solves the issue of sulfate concentration. The higher sulfate concentration, the highest the disturbance between the sulfate, total sulfate, and sulfate present in alkali sulfate. So here, what I did, I calculated the sulfate coming from gypsum and the sulfate present as alkali sulfate. So I disconsider the sulfates incorporated in alide and belide. And I run again this analysis, and now I see better correlations, especially, but first, not with immediate C3S and C3A. This also was not good enough, but I saw a good correlation with alkali. Again, the exception is PCG, I will explain later why I like this, but we see a great correlation. The greater the alkali, the greater the optimum sulfate content. Because alkali increases Clinker reactive, meaning more CSH, absorbing more sulfate, and meaning more ethylene consuming more sulfate. So we accelerated sulfate consumption, so we increased optimum sulfate. PCG, again, was an exception. Why? Because PCG, as I explained later, had a very high silicate peak. This means that it has a greater alide reaction. I don't know why it has a greater alide reaction, but it has. So a higher alide reaction means more CSH, more sulfate incorporated in CSH, so more optimum sulfate content. The other way to analyze the sulfate amount is this method proposed by Franco Zunino and Kari Silva. And we saw here for all 8 clickers here on 4 that we have a great relation between the total and the soluble sulfate content and the heat release until the onset of luminosity. And here we got the X intersection and the slope, 2 parameters instead of 1 to evaluate. And when we evaluated the relation is the X intercept and the alkaline, we see a good linear relation, and now we don't need to exclude PCG from this regression. All of them agree well. But in PCG can be explained by the slope of the silicate peak. That correlates very well with the slope of the regression. So now, putting 2 parameters from this analysis, I can explain all my clinkers. So we have a great influence of alkali content and also from silicate reactivity. So the conclusions of this study is that the optimum varies a lot between the clinkers, but there was a very strong linear correlation between sulfate and mineralogical parameters, indicating that we have several different simultaneous factors. There is strong correlation between optimum sulfate and the sulfate on clinker, because not all the sulfate on clinker is soluble. We see sulfate incorporated silicates probably don't participate in the first 12 hours of hydration, maybe some part in a life, but especially not in the life. So we should disconsider the sulfate. Alkali is a critical factor because increases C3A in a light hydration, so increases sulfate demand. Ethylene forms even without gypsum, showing that indeed some part of the sulfate in clinker participates in the reaction. And so the indication is that the sulfate optimization should target soluble sulfate instead of total sulfate. In terms of the white clinker, we saw a sharp and early illuminated peak. We had the hypothesis that the absence of C4AF and more for indentation phase, so leading to faster CPA hydration. It's confirming this information. We also saw that conventional methods total heat was less reliable. I'm going faster now. So this is the first article that we have, that is the Clinker practice, statistical mixture design. So we have the 6 great Portland clinkers, a subset of the 8 that we just used. We did a design of experiments resulting in 21 mixture. We use the same as sulfate content, 4%, because none of the clinkers was undersulfated. And we run isothermal calorimetry, lab XRD, TGA, and compressive strength. So here's the 21 mixers. We have 3 of them that is equal, the centroid, to see the variation in the error in each measurement. We also have 6 of them that is only 1. So here's the calorimetry result, great variation, length, fat, time. And here we saw that the error of the calorimetry, because we have 3 mixes that are equal, but I run in different days and weight at different days, and we see the error. So this variation by indeed significant. Also here the XRD results at 1 and 28 days, 58 degree of hydration, PSH, Portlandite and guide, PGA, bone water in Portlandite content at 1 and 28 days, and the compressive strength at 1 and 28 days. So I got all of these and try to correlate everybody with everybody. So first of all, strength and heat at 1 day, as observed in the first study in the literature, but I don't see a good relation between strength and bond water, because I have different clinkers with different mineralogical compositions. Here I see the correlation of the properties that I call with each clinker. I highlight here again the influence of alkali in the initial reactive of clinker. The alkali controls influenced a lot the first days of hydration. We didn't observe an influence of C3S for the fish, neither in calorimetry or in strength. So we don't saw that. C3SN1 was not more reactive than C3SN3. In fact, when you have more C3SN1, you usually have less alike, less C3S. So the clinker was less reactive if you take globally. But we didn't see a greater reactive of C3SN3 or N1. In terms of strength, TCF has this with day and TCD negative correlations that align well with the data. The low strength of PCB is explained by the low C3S content, the high phosphorus content, and the large allied crystals. But we cannot explain why PCF has a good strength, because it has large allied crystals and low allied content. And we cannot also explain the low performance of PCB, likely due to uncontrolled factors like quenching and allied crystal defects. At 28 days, the most influential one was PCB, while PCB had moderate negative correlations. PCF was big correlations. So at 1 day, no strong correlation with mineralogical was found. So to increase the 1 day reactive that we want, high blended cement with high amounts of supplementary cementitious materials, at least if this group, it's not only the C3S content that matters. This is not saying that the C3S content doesn't matter, but it's saying that other things also matters. So the small group by phase reactive in the phase content itself. At 28 days, we can see now a good relation with allied C3A, C2F, and C4AF. In general, CFA had a moderate relation with its strength at 1 day and 28 days. So overall, it's very composition and active factors other than the group composition itself. So I run some models here, so to try to predict the heat peak, the setting time with our Portland clinkers. I will pass those to station, but here we see some models to predict the heat release after 1 day with our 6 clinkers that we analyzed. And here output compressive strength at 24 and 28 days. In general, we obtain good models with very good statistical results, showing that we can use this statistical mixture design to optimize our cement if we have different clinkers. So, alkaline was the most influential factor on hydration. We didn't see influence of CPF for this, with correlation with compressive strength, meaning that it's driven by phase reactive and microstructure instead of only view composition. So we cannot use properly phase alone to be a predictor of compressive strength. We obtain strong predictive models that capture the nonlinear interactions, but was limited because we don't have all the parameters. We don't have the processing parameters. So mixed design was effective and could be used to optimize it. So this was my thesis, structured in these 4 papers, chapters, and the overall consideration that we investigated the influence of Clinker chemistry and mineralogy on hydration, sulfate demand, and mechanical performance, using 4 different studies with a multi-technique approach. XRB, lab, and single isothermal volumetric, PGA, and compressive strength. With this, we can conclude that challenge the traditional view, viewed phase content, the amount of halide, the light, CTH, and 4F, is alone is insufficient to explain reactivity and strength. Instead, we must consider polymorphism, sulfate, type, and microstructure. The scientific contribution, we have a deeper understanding of how the composition goes from hydration, sulfate demand, and strength. And practical implication, we contribute to obtain rational design of more reactive and robust clinkers. We contribution for the sulfate optimization in all these aligned with. So I want to acknowledge first UDESC and the PPGCI in these labs for the infrastructure. I also want to acknowledge UDESC and Erich for some of the experience was run over there. Also CNPq and Cimentos for the scholarship given to me in these 4 years. I also want to acknowledge my family, my fiance that is here. Thank you very much for all this care, support, and love given to me these last 4 years. It was very important for me to achieve this. Also, the group, Lindsay, first of all, my supervisor, thank you very much for all the care and the support to open so many doors to me. It was very important. And all my colleagues that helped me a lot, especially I want to acknowledge the undergraduate students that helped me grinding, stopping hydration, and many things. So thank you all. You are family to me. I also want to thank my course supervisor, Paulo Ricardo, that is a modern supervisor, a partner at UDESC. So thank you very much for all the contributions, especially in the XRD of this thesis, but also the partnership in all the projects. And also his group at Joinville in Nîmes that run a lot of XRD analysis for me. And I want to acknowledge Aldenori, that's a great place for me to be here. I want also, I didn't have a photo, but to acknowledge my friends at UDESC Laguna, so Márcio, Fernando, Christian, Aline, Paula, and all the professors and my students over there as well that helped me through these years. I want to acknowledge Intercement, especially Suzuki, Daniel, Dennis, and Ricky for the help and the many discussions, technical discussions, and the point of view of industry was very important for me. So, and also for XRF analysis and XRD analysis, thank you very much. I want to thank you, Sylvia and the team, for providing me very valuable data that we use and was very important for this study. Also, I want to thank you, Ifu, that was very important to this PhD thesis that helped me a lot in different process, and Sakata that was very important in when we went to Singapore. So this is the Singapore thing. We went over there 3 times, so thank you very much. I also want to thank the examination board. First, Ruben Studies, it's an honor to have you here to evaluate my work. Also, Sylvia and Suzuki, it's very valuable for me to have the practical view of the industry. It's very important to develop science that is not only academical, but that could be used in the industry. So thank you very much for your participation. Thank you, Erich and Pasuelo, for the time. I know it's hard to read, to have time to read thesis, especially Erich that came from Santa Maria to be here. And thank you all for the time and attention. And that's it.
Parabéns. Congratulations, José. So I want to invite the committee to sit here. Please. Thanks for being on time. Not like. Senta aqui também. Eu acho que eu sento lá e aí vocês sentam aqui e a gente coloca a câmera. Erich, tu tá mais perto? Eu acho que eu acho que eu senta aqui, ó. Tipo, José. Se vai ficar aqui, ó. Vai ficar melhor. A coxinha com os olhos, com o cachorrinho.
Pode, se quiser, pode comer também. Trouxe para vocês. Obrigado. Pode ser, claro. Pode passar. Pode pegar. Não, obrigado. Sorry, guys. Anna Paula just went to the bathroom, so we have a 5-minute break, perhaps, before the. Unexpected.
Sim. E assim, pergunta para eles se estiver dando normalmente. Okay. So. Não, acho que tá bem aqui, né? Eles têm que deixar só um pouco. Mas tá ligado, né? Tá. Ok. Okay, we are settled now. So thanks again for participating on this committee. So the next part, I'm gonna to leave to my colleague, Paulo. First, José was very clear acknowledging all of you guys. So I also want to thank for being here. And I want to invite my colleague, Paulo. José was his first PhD, so I will give the honor to conduce.
Okay.
Okay.
Well, thank you so much, everyone, for participating in this committee again. We have a very broad committee in terms of experience and application. We are very glad to have both the industry participants, Silvia and Suzuki, and the academic part. So especially one of the most known reference in XRD, Ruben. So thank you again, everyone. We know that it seems that every time we have less time to do things, so take some time to read a PhD thesis is really we really appreciate that. And we used to start the second part usually from the furthest member. So for obvious reasons, we would like to invite Ruben to take the time and ask Jose questions and discuss and take the time you think it's suitable. The floor is yours, and thank you everyone again.
Thank you very much for the introduction. Thank you also very much, Jose, for the interesting thesis and the invitation to be on your evaluation committee. It was a pleasure to read your thesis. Maybe just for my information's sake, is there a time limit set on the questioning of? So have in mind that I don't go over time. Is there any regulations? If not, then there is. I will just start and we see where we end up.
No, you can take your time, Ruben. At least we want to finish. Yeah, so it's up to you. Take your time.
It's, everybody has like fixed amount of time.
Yeah. So
okay. We can go ahead and see where we go.
Here sometime people talk like around 1 hour, but maybe maximum 40 minutes. It will be okay. But feel free to talk.
I don't think it will take that long.
Okay.
I mean, just here, Leuven, like defenses only take 2 hours in total.
Here,
jury member, so you have to mind a little bit.
Okay.
So I can go ahead. Thank you. And obviously already maybe go through things that chapter by chapter, paper by paper. So the first paper or results chapter is chapter 3, and I had a question there when you are actually looking at the page 441.
Just a minute, I will.
I was wondering, even if you say that there is the experimental data come from the industrial collaborator, if there would be any means to explain a little bit more in detail what would exactly be refinement procedures. My main concern or issue is that in terms of for the homogeneity of our thesis, in which in the next chapter you say really clearly, well, this is very important to do this in the right way. I think it would be good to provide a little bit more detail there. Maybe you can discuss this or add a few lines maybe in an appendix to detail two things. I was mainly interested to know a bit more about, okay, how was the XRD analysis done? And could there be, obviously, because that's a question that you may ask, could there be any effect or impact on how that was done on the results and on the regression analysis that you eventually do? So maybe more information and a critical reflection would be of interest there, but maybe you can already say a few words about that.
Okay, thank you very much for the question. It's a very good one. So this was a great limitation that I had during the thesis. This wasn't planned to be on my thesis, this chapter, but Paula, as I said, opened many doors. So we got these results and we saw these results, and it was very rich for us, like many data. So she talked with the industry and they could share with us the data, and I analyzed. So the regressions and all the analysis I done. But unfortunately, I didn't have the raw data. I even asked the raw data of the calorimetry, the XRD I analyzed in the same way that I did in the other chapters, but they didn't have the files. So for instance, I only could do the correlations with total heat, but I couldn't, for instance, go to the inductive land, to silicate, sulfate depletion point. That would also be interesting. And the main limitation is the XRD, as you said. This was done obviously for the 40 clinkers was the same. It was in the same equipment, in the same routine, but has several limitations. For instance, the alkali sulfate fragments. They put all the clinkers had aphthalite and arcanite, and all. When you include in the refinement will give you like 0.1, 0.3%, even if you don't have. So, and also the C3S polymorphism, I think, was a great limitation, because we saw in the chapter 4 the great influence on the analysis and the XRD setup. So unfortunately, I don't have the raw data for me to do the same analysis that I did in the other. But we said, okay, it's a very rich data that we can analyze, but this indeed is a limitation. I worked something about that, very discreet. Maybe I could be more incisive on the C3S polymorphism discussion, saying that we didn't found very great correlations, perhaps due to the limitation in the quantitative based analysis. But I can obviously go deeper on this, put more information in an appendix to be clear.
Yeah, I think just for I would not redo all the analysis because it's not what my question is aimed at. I think it more I need to explain a little bit more background on why you do not have more information, or at least share that it's been done with, say, one mother kind of file, which was reset in a way that it is very consistent, yet may not capture all the details that you later on have identified as being of interest. But then, as you say, it's indeed a rich data set, and it's a consistent data set, which also has outside for the regression analysis that you did afterwards. Similarly, maybe also just a bit more detail on, I think, and there that should be possible retrieved from the companies on how they actually measure the crystal size, the halides. So optical microscopy, but it's not really mentioned how the samples were prepared or how they have measured or decided what is the average crystallite size. So
okay,
I suppose there is probably a standard that you can refer to that might be pretty easy to do, but it's a little bit on the same line as regarding the XRD analysis, but a bit to the side.
Okay, the optical microscopy.
So my follow-up question that was related to a bit deeper analysis is then not valid. It was obviously interesting, but maybe you can also comment on that from a different perspective or out of your experience in different chapters would be. So crystal size of halide seems to have a significant effect. In some of the correlations it comes forward as being quite important. And then there's the hypothesis that the bigger crystals have less defects, right? So hence they react a bit more slowly than small crystals. I think you also really know pretty well that with a more advanced XRD analysis, it would be possible to test that hypothesis. So I'm not sure if you have tried to figure that out in subsequent chapters, but crystallite size and strain combined with crystal size, are there any correlations? Are there any relationships that you expect there? And can these support this hypothesis of defect density controlling? Be an underlying reason of slower activity of the clinkers?
Okay, this is a very interesting topic that we want to investigate further, obviously. So we saw this correlation, and there is no many papers talking about that nowadays, but we go back to the 90s and we saw Taylor's book. They said, oh, there is a great correlation between crystal size and strength and reactivity. So I hypothesized that maybe in the grinding, if you have smaller crystals, this would be have more defects affecting the edge pitch formation and therefore increasing clinkers halide reactivity, but we didn't confirm. So perhaps it's a very good option, a very good idea to go deeper on this, on XRD analysis, other analysis, to try to calculate or to identify the amount of defects on a light, and if there is a correlation with the size of the crystals or the reactivity, but we didn't do this. So we determined the crystalline size of a light in XRD that is different from the crystal size in optical microscopy, but maybe indicated the effect. But I didn't run any analysis on that. Maybe there is a lot of things I didn't think about that, but it's a good idea. I will do that. Yes.
That's the hypothesis to try and delve into that topic. But it's good that you thought about it. That's clear. Reading a bit further, that's on page 44. You mentioned some of the specifications on cement and clinker composition in Brazil, which are quite different from those that we have in Europe, particularly when we look into magnesium, but also sulfate, magnesium oxide and sulfate content. It's more out of my own interest. How does that come about that these specifications are so different? Because in Europe, well, these are, let's say, prescriptive limits that have at some point been defined out of, well, maybe compromise, but at least there must have been some underlying data saying this is safe and it is not so safe to go above. In Europe, for instance, the magnesium oxide of 5%. So, can you comment? Because it's interesting. I mean, also in terms of development of new binders. Maybe in the Brazilian experience, there is no issue with softness or suspension when we have more sulfate or more magnesium oxide. Or do I see this wrongly? And is there another test you should do so you can be safe that sure that there is no risk later? Can you? Enlighten me there.
Yes, so this is also a very interesting topic that I observed that usually the optimal sulfate on the European clinkers, papers, and all things was lower than the Brazilian ones. Here is usual to have clinkers, the optimum sulfate being 4.3, 4.4, even 4.5, that is the standard limit in Brazil. So this I start to think about that, and maybe it's due to the sulfate coming from clinker. So if you compare here, if Argentina, they have less sulfate in clinker because they use natural gas as fuel. So here in Brazil, we use a lot of petroleum coke with a high sulfur content. So our clinkers has a lot of sulfur on it. And then the limitation here, the limit is 4.5. In terms of magnesium, the limit is regarding periclase in cement. So what they do is to dilute the clinker factor on cement to achieve this. So we have a 6.5%, if I'm not wrong, limitation in the periclase content on cement. If there is problem or not, I don't know. I think we need to investigate more. First, in terms of magnesium, talking with the guys from the industry, this comes from a necessity. We have a lot of limestone with a high content of magnesium in the south of Brazil. So to make cement, we need to produce with this limestone. So this is the reality in the south of Brazil. Many cement companies do like this. And usually we don't have problems with the soundness of cement or something like that. Talking with the cement company and also looking in the literature, maybe they say that the soundness, the expansion given by the magnesium is used usually when you have magnesium clusters. So if you grind very well the raw meal, you have the magnesium diluted and won't have a soundness problem. So we, in fact, want to do more studies on that to confirm or not that is indeed the cluster of magnesium oxide and not the total amount of magnesium oxide contribution to the soundness of cement or not, because there are in some cement plants, they need to go above this limit in the next years, because the good limestone without magnesium is finishing. So, or they close the cement plant, or they use the limestone with more magnesium to go even above these ranges. So we want to evaluate.
I think that is interesting and also quite important research that can be done, because in Europe also we see that these prescriptive limits are maybe coming forward from an era where Portland cement production was done in a certain way, and that actually we need to move away a bit. And it's not always really very much linked to expansion or soundness issue. It's part of a broader discussion that we have here also when using different types of SEMs. They may also contain more magnesium, or you might want to use, for instance, in the case of sulfate, more sulfate typically, because you have more aluminates and so on. So in that respect, I think it's important also to think about the test methods to assess, because soundness is, we have this less Chatelier test in Europe. I don't know what you have in Brazil, probably something similar. But yeah, we are starting to doubt how relevant this test result is for the actual risk during service life. But working with these higher levels of magnesium and sulfate and maybe not having issues could be a very good argument to revisit these numbers. Okay, right. I would also like, if we go a little bit further, I think you already commented on that in one of the in one of your responses is that it was difficult to differentiate M1 and M3 in this first data set. Yet, maybe in more general, to what extent do you think the C3S M1 and C3S M3 scale factors are correlated? What is the covariance if you would look at these in your studies? Because you see very often your C3S total is, when changing maybe refinement procedures, data source, etc., is rather constant. Rather constant, not always, but C3S M1 and C3S M3, yeah, they seem to be like communicating vessels. So, and I sometimes have discussions here on, yes, okay, how reliable is the quantification of the polymorph really, and maybe an extension, how important is it in view of your conclusions?
So thank you again. You are bringing very good discussion topics, and it's indeed the C3A is easier to properly identify, but C3S is quite difficult. So especially two monoclinic structures that only change the shape of the peaks and everything. So if you always include the C3S polymorphs in your refinement, even if you put a homoadric one, the mathematic will show some participation on that. So we need to first evaluate it well. If there is M1 and M3, we have some strategies. But as you said, if you have both, it's quite difficult to properly quantify if you have 20, 25, 30, 40% of M1 or M3. It's all mixed together, and the structures are quite similar. And if you refine the scale factor, if you refine the crystalline size, everything will blend together. So I don't see that being a very, how can I say, precise quantification, especially in industry, as you have lab equipment without monothermometer using a ritual setup over there, without a proper guy looking to the secret. And I don't know if it's important, but here in Brazil, the industry has this view that M1, C3S M1 is more reactive than M3. I don't agree, based on my results and based on literature. But here, all the Cimentos to increase C3S M1. So this is why I spend so much time looking for C3S M1 and M3 and discussion. But I don't see that in pure phases or in booster phases. And also talking with a guy from Latin America, but not in Brazil, they are including magnesium in the raw milk to form more C3S M3 because he thinks M3 is more reactive. So I as a scientist, I don't know if C3S M1 or M3 is reactive. Doesn't seem to be only from the polymorph. We have like 2 or 3 papers in Silent and Concrete Research, old papers 20 years ago saying that M1 is more reactive, but we have a lot of papers on pure phases showing that depends a lot on the size of the crystals, of the crystallinity, the ion that is incorporated, not the polymorph itself. So I don't think it's very, now, with all the results that I have, that is very important to differentiate M1 and M3. I think it's better to have like certainty about the amount of C3S and the crystal size of C3S and perhaps the effects on C3S and the ions that are incorporated in C3S rather than polymorph itself. But it's a discussion that I will continue to study to see if it matters or not.
It's of course also a bit of a limitation of regression studies if you have a large data set, is that how to differentiate correlation from causality. What is the underlying cause? Because you have so many parameters. And say if you that might be interrelated. The magnesium might affect the polymorphism, but might also affect the total content, etc. So yes, it's sometimes difficult to disentangle. But anyways, I think you did already a very good job in discussing all possibilities there. It's good that you have this challenging, that you challenge the way of thinking, try to investigate what would be underneath. What maybe is also some conventional wisdom, but I don't see you challenge it. Is neither in chapter 3 nor chapter 4 is comparing your results on quantitative XRD with I think what you know what is coming with bulk or modified Bohr calculations, or call it mass balance.
Yeah.
So have you tried, or you just don't believe in Bohr calculations at all? So what's the what about Bohr? How does it compare to?
Okay. Yeah, this is, in fact, I think about to include it, especially in the first chapter, because we have a lot of clinkers. We publish let's say Congress paper about that, comparing both with the 8 clinkers. It's a very small conference here in Brazil that we published this. But yeah, we all know the limitations of bulk, right? There is some refinements in bulk to correct, but we don't consider the incorporation of minor elements in halite and belite, as I showed. Halite and belite incorporates iron and alumina. And what I saw is a great discrepancy in some. C4AF was okay, I think, with the iron compared to the other phases, but especially the C3A, because the incorporation of alumina in belite. So I saw the biggest difference was the C3A content, because much of the alumina incorporated in silicate and especially in belite. So I think it would be interesting perhaps to add this as appendix comparing this XRD with both, because I already did this, but I decided not to include it because it was already very big, larger papers in terms of words and results. So I prefer to omit it. But I think it's important because some cement industries still using. Here in Brazil, they are acquiring more and more XRD to run the X-ray deflection, but yet a lot of cement plants in Brazil uses bulk equations, and I think it's there is a lot of limitations.
But maybe it's a good idea to at least communicate about the results towards the local industries. Maybe not in your PhD, but in a more accessible, I don't know if you have an accessible cement journal or something.
Yes.
To inform that, yes, if you are using alternative fuels, alternative raw materials, that you might get a lot of discrepancies. Yes. Regarding chapter 4, I'm not going to ask many questions because we collaborated to some extent on that one, and there was already an exchange about it. Yet I still have I mean, you provide some advice and guidelines on quantitative phase analysis by XRD. And one discussion I'm having here with some of the students is as well, if you think, and my question is there open, if you think that there is any impact of the specific refinement software or routines or algorithms that have been used in those softwares and the outcome is this. Do you think this is a significant factor influencing the results?
Also a very good question. We are having this debate right now in Brazil because we have access to topics, but it's not easy for everybody to have. It's very expensive, especially for us in Brazil. So we were in a congress 1 month ago, 2 months ago, 1 month ago, no, 2 months ago, and we were talking with the guys from professors and students. Paulo gave an XRD course over there, and we were talking about that. There are some free options like GSize, Profex, and other options in the market. And it shouldn't impact, but I believe it impacts in some extent because you have some features in some softwares that you don't have in others. Paul can correct me if I'm wrong, but in Topos you have like the full parameter approach that I don't know if every software has. So I believe we need to do some work on that to compare the results between softwares. But I believe that there are some refinements, strategies, and options that we use in some softwares that the others doesn't have. So I believe it impacts. I don't know how big is this difference, or if there is ways of minimizing. So we are currently using.
It is indeed part of this fundamental. Well, sometimes it's indeed the equations of the algorithms to do the peak shape functions. But I'm also having discussions about, okay, these softwares, they use routines in which they first say refine scale factors, and they do this, and they do that, and then they come back in another cycle. And they don't do this in the same way. The question is, and there should not be, of course, we don't want to have it, is there any path dependency? Is there any routine dependency? So we're also still a bit struggling with that. And of course, any software you use, these are complicated software packages, requires very good control on to know exactly what you do. I think you have used Topaz, not Topaz Academic. So I've used several softwares. They all have their ways, and yeah, it requires some time to master what's the phase analysis of Clinker, even if you know, or even if you think you know how to do it in one software. It takes some time to get to similar results in other softwares. And I think that this is one of the challenges that maybe researchers should also try to help with is in providing more guidelines for specific softwares, or highlighting what is specific to be paid attention to. Okay. Yes. Then chapter 5. I was reading with interest. So you've done in situ XRD there, combining it with heat flow experiments, and coming with some interesting results to support the sulfate optimization results. There's some things that I don't fully understand yet, and may also relate to my previous comments regarding some mass balances. When I was looking to page 150, for instance, I couldn't help but notice that the C3A consumption seemed to be rather modest compared to the formation of some of the AFT of the Ettringite phase. I didn't try to calculate the mass balance myself, but I was wondering if you checked whether the consumption of C3A that you see there could be explained by the formation of Ettringite could be explained by the consumption of C3A. In some other papers, this decrease in C3A is a bit more clear, for instance, around the sulfate depletion point. In your case, it seemed like a continuous, most of the cases are more like a continuous sloping down line. Do you have any comments or ideas about
thank you for bringing this.
How to explain this?
Yes, so we had some difference that I noticed is that the C3A didn't decrease as expected. So I ran again and again, and it didn't happen. And also the AFM, I think it formed quite early than expected, because in in a lot of papers, you have the first gypsum depletion, then you have some time and AFM formation. In this case, the AFM started a little bit early. I confirmed looking to the X-ray diffractograms that indeed had a AFM peak before gypsum to extinct. So what I didn't run the mass balance calculation. I will do it, of course, it's very important. But these results I will redo again, because when we went to the single-throw XRD, they were still processing the software to process the data and form the X-ray diffractogram. And we were the first one of the first users in the line, so the algorithm, the software was not good enough. So our X-ray, especially at low angles, is not good enough. Like the gypsum peak is quite weird and this kind of thing. And I was waiting for them to solve these problems to have better diffractograms. And they give me a yes signal like 1 month ago to 1.5 month ago. And I couldn't do it for the defense. So I will redo the analysis with this better data and also check the mass balance calculation, because for me it was also weird, because I think it's a very small C3A dissolution to form so much at the guide and then it's stable. So I will do again with the better data, better diffractograms, and I will check with mass balance calculation if it makes sense.
Yeah, okay. But, and I think you also have next to it the heat flow data. So there are some examples, some papers where they also try to figure out whether, okay, and that will not be one-on-one possible to figure out whether you can, by defining these reactions and discretizing them, calculate what would be the heat production as well. So that could also be an interesting one to sort of check the hypothesis of the sulfate equation. Yes, and then, well, I think it also comes together with checking the mass balance, because yes, the sulfate sorption is very much also coming a result of doing such a mass balance and finding out that, say, sulfate is missing when we look into the amount of ettringite which is formed. And well, I think you make a very interesting contribution, noticing that alkalis impact the amount of sulfate you need in cements, and that this is related to the reaction rates of the CSA, of the C3S and so on, producing more CSH. And that might be so, but it would also be interesting to try and quantify that a little bit more, with trying to provide some CSH contents. But it might also be related to of course, the specific surface area produced by the CSH, by a given amount of CSH. So the way it grows, the way it nucleates and grows, and this might be also changed by having a faster reaction rate and a higher pH. And in addition to that, probably you can mention that or take that into account as well. Sorption is of course also pH dependent, so it could be the alkalis, soluble alkalis, affect the pH of the solution. That will also lead to a different sorption of sulfate to a given amount of CSH. And I think there's some work you can refer to and you can also use to help interpret your results. Maybe on chapter 5, but I understood that this is maybe not yet the final. I didn't really understand how temperature was controlled on the in-situ XRD. Is there a temperature control to make sure that the calorimetry and the in-situ data are done
Unfortunately, no. Yeah. The secretary, they have the room at, yeah. Like all the room is kept as 21 Celsius degrees.
Sorry for interrupting, Ruben. In the synchrotron measurements, there was no specific device, but the measure was kind of quick, like 1 minute. So
1 minute.
Not.
And they changed the sample, and the whole room was 21 Celsius degrees. Yeah, but you didn't have a sample holder temperature control. Yeah. It was only 1 minute.
So more or less.
More or less, yeah.
and 21 degrees, I think that was the same approximate.
Yes.
Yeah, just be careful that it's not too difficult, because then things of course start shifting. Yeah. That also brings me to another interesting question, more general question is, so we do sulfate optimization at a given temperature, right? But I know in Belgium it's 15 degrees maybe, today it's 25, so maybe it's not a good example today. In Brazil it's often more warmer. So yeah, I think the method it always refers to 20 or 20 degrees. So and actually 20 and 30 or 35 degrees really can affect the hydration rates of different cement phases differently. C3S has a different activation and C3A. So how should we deal with sulfate depletion in different climates?
Is also a great question. And in fact, here in south of Brazil, we have a great variation in climate. So here now you add the winter, so it's like 10 Celsius degrees, but it goes up low as 3-4 Celsius degrees. And in the summer, it's like 40 Celsius degrees. So in the city that we are here, Porto Alegre, we have this problem in the seasons. So what we optimize a cement to the winter will be the same content for the summer. And not only the temperature, I present a paper in this Congress 1 month ago, and was very interesting to have a lot of people from the industry over there, and was people from the admixture companies, and they say, okay, but you optimize these, and I will include the admixture to do the concrete, and will change everything. Or I will, in USA, they add the supplementary cementitious materials in the concrete that will also change the sulfate content. So I think it's a very intriguing and difficult question. I don't know how to solve this. What I said is usually better to have, obviously, then inside the limit of the standard. I believe it's better to add a little bit more sulfate to prevent sulfatation than to have this problem. So I would say that, okay, optimize for the worst case scenario, and if you don't, the worst case scenario would be the one needing more sulfate, probably a higher temperature, and then you need to, if don't pass the limit in the standard, use this. You know? I would say that, but I don't know. I think I need to think more about that to see a solution, something like that. But this is a very interesting topic.
That's an interesting topic in particular. So Portland cements or Portland cements, that's one thing. But if you move towards blended cement, composite cements, and you start including podzolans, it becomes even more important because their activation energy is really quite different compared to the ones of the clinker phase. So we've done some research as well there, and you can see that, let's say, 20 and 40 degrees, you would require different sulfation levels. Composite cements, so it's an important topic. Yeah, maybe to find out the discussion on that chapter, you have used the method proposed by Zunino and Scrivener to evaluate or study the sulfate dependency or the sulfate requirements, but it wasn't clear to me how are you going to do sulfate optimization with this method? Is this useful, or is this method useful for that, or it should not be applied to this?
Yeah, it's not like I expressed myself in the wrong way. It's not a method to optimize sulfate, so you don't obtain an optimum sulfate content. It's more additional method to try to understand the sulfate balance, but you don't optimize sulfate buying. So perhaps I need to rewrite something. Then even in my presentation, after I speak, I think about that. It's not an optimal sulfate method. It's just to try to explain what is happening in the sulfate balance, but it's not to optimize sulfate. Paulo wants to speak a little bit.
I would agree with that, but maybe it can be a better way to find it. If it's fun.
Paulo wants to.
Sorry.
It should be compared to some.
Sorry for interrupting, but we often come back to this discussion because the optimal sulfate content will depend on to what age do you want to optimize. So for 1 day's range, 3 days range, 28 days range, and now the temperature variation that you mentioned. So the actual ASTM method using the total heat vary depending to what age you want to optimize. So the method that Jose used and is what Karen do also is to just ensure that the illuminate reaction will occur later. It's kind of sad because it's very operator dependent, right? It's not actually a systematic method, but we saw that as an alternative to not fall in this philosophical question, like to what age or what method do you want to optimize systematically. But we agree that it may vary on who is doing the visual analysis, right?
I mean, I see the value of the method in studying sulfate balance or sulfate requirements of the cement with the slope, and I appreciate that. It's an interesting approach of this. I was just wondering, okay, can we use it and how can we use it further? Okay, I think I've used quite a lot of time already, so maybe just one last question about chapter 6, about your statistical design methods. I think maybe you need to explain to me once more what is the point maybe of blending these clinkers together. Is this, why did you do this? And what is the potential application of that?
So to be clear, in my head at the beginning would be better because, like, I don't know, the first, the idea, the concept was, this is a method that I use for optimized blends in some, for example, concrete, like you have silica fume, cement, two types of cement, sand, water, and you want to optimize all of them together and see what happens. So I had the familiarity with the method, and in my mind, at the beginning of the PhD, I thought, okay, I can blend 6 clinkers to obtain 21 mixtures, so I could have more variation and try to see correlations that would be higher points, more variations than only 6 or 8 clinkers. So this was my idea. Obviously, you have the fact that you are blending only 6. So you can see clearly. It's not the same of having 21 cements different, because this 21 is came from 6. So for instance, the PCB has a lot of phosphor and the others doesn't. So if you correlate phosphor, will be a good correlation with everything, but because you only have one clinker with a high phosphor content. So the initial plan was to study, to try to see if I could see some correlations beyond the 6 clinkers, but then the causality that we only have 6 clinkers to form 21 mixtures impact on that. And for the industry, I thought that maybe, okay, you have some clinkers from different cement plants, and they have, or even like in the same cement plant, you have variation in the clinker during 1 month or 1 year, and you want to see which clinker is best for, which variation is best for compressive strength, or if you could change the raw mill and the process to form a mix between the two samples, you know, like, or in May I had this clinker with very low C3S, and or in June I changed the fuel and I have this. So this is better than this, or intercomposition. So was this, at the end, I'm not very happy about the result. I think in my mind would be better because I could see more clearly the correlations. But yes, this was the idea.
Okay, thank you. Thank you for
Thank you very much.
And thank you very much for the defense and the nice discussion.
Thank you very much.
Happily give the word back to the chairman. Thank you very much.
Thank you. Thank you very much for your valuable contributions. I will continue to work on these topics because I think it's very important to clearly understand all of this. Thank you very much.
Okay, thank you so much, Ruben, for the arguation. And I don't know if this is the word in English, but very, very interesting questions that some of them at some time of in the process we also faced, but I took some notes here about the crystallite size and strain of the halite. We for sure can look deeper on that, maybe mixing some lab synthesized and industrial clinkers to try to find some correlation on that. And anyway, all your points are noted here and we will discuss. And of course, we will keep discussing the topic with you. So we will pass the word for the next member of the committee, Silvia. We have the honor also to have Silvia here, a huge reference on cement industry here in Brazil. So Silvia, thank you so much for accepting the invitation, and the floor is yours, and take the time you need.
Thank you so much. I have to say I'm very honored and happy to be here. José has been doing a great work, and this is what I would like to highlight at the beginning of my comments here. I was really impressed by the number of publications you made during your PhD. It's really amazing, and that alone showed to me that you are ready to get your PhD degree. So I'm spoiling now the whole stuff. I really was very impressed by the work you have done. The thesis itself is a very valuable material for us from the industry. I think my colleagues say Suzuki will agree with me. A lot of very good information. But to start to put some heat on the discussion here, I want to take a topic that was mentioned by Ruben regarding magnesium. I had realized that I think you were working with the previous version of the Brazilian standard. And nowadays, the Brazilian standard is even more flexible in terms of allowance of magnesium in the cement. And nowadays, the only restrictions we have are for cements with no supplementary cementitious material. Type 1, Type 1S, higher strains with only 10% of limestone feeder added, and white cement. For the rest, we have erased any kind of restriction. I participated in the discussion when we made the revision of the standard in 2018. And the reason for taking the restrictions out is one, already mentioned, in many plants, especially in the south of Brazil, we have very high magnesium in the limestone that leads to clinker and, of course, cement with very high MgO. And we did not have so far one single case of durability issue. So I think the history shows that we are on the safe side. And going back a little bit to literature, we realized that the restriction on MgO is more kind of pre-concept than really a technical one. I think maybe it's because in 1884, we had some problems in Europe, especially in France and Germany, with cements with very high, so magnesium very high, I'm talking about 30%. And then we had the expansion. And then created this issue regarding magnesium expansion durability. But the real exposure conditions show that this is not the case. So nowadays, the Brazilian standard almost erase all requirements regarding limits on MgO in cement, except for those with no supplementary cementitious material. So that's one point I would like to highlight. I like very much the thesis itself, especially the parts that are bringing some novelty regarding to what we know or what we do today. And then, for example, the last chapter with this, you just mentioned that you did not like the results, but I like very much the methodology. I even forward your thesis to my colleagues to see if we can implement the methodology to do some optimization during our product development here at Cimentos. So I think that has a big value. Is a new way of looking at product optimization because can optimize our resources. I really do not believe that we can mix clinkers. I think that's out of our reach. But maybe to work with different supplementary cementitious material and get to properties we would like to have, probably is a good tool. One thing I would like to see a little more in discussions are comments on kind of not unexpected results, but that goes against what we believe as a common knowledge. For example, the influence of B-light on grindability. We at industry, we believe, or maybe, I don't know if this is the right word, but that B-light has a strong impact on grindability. And in your data, it does not show it. So as is not expected, maybe would deserve a bit more of comment and work. So what would you tell me about it?
Okay, thank you very much. The first commenting about the first commentary, this methodology is very good. At the end, I wasn't happy because, as I said to Ruben, and as you said, doesn't make sense to blend clinker to types of mice. So wasn't this sense? I went to see correlations and at the end didn't work. But we also run some this method to optimize mixtures, for instance, in self-level concrete, where we use different materials, and it's quite good because we don't need to spend a lot of time. We can reduce the amount of mixes. So I believe for SCMs could be a good option. And yes, I believe I could be much further in the data, especially in the first chapter. We have a lot of data, very nice data. So at the end, after I published the paper, I thought, oh, maybe I could do this, I could do that. So yeah, this is very interesting. In terms of grindability, literature also say that the light is harder to grind than a light. And I saw a weak correlation. Yeah, if you see the grindability, the light is in the negative and the light is in the positive, but it wasn't the main factor. The main factor, if I record by my head, was the sulfur. So it's like Ruben said, maybe it's a causality. Like if you have more sulfate, you will have more B-light. But the sulfur, I believe, changed grindability because I changed the viscosity of the melt. So probably it's changing the porosity of your clinker and is impacting more than the phase itself. So I believe the light impacts, but perhaps you have other things impacting more than the light and the mineralogy itself. But I believe I could do a lot of more analysis on this data and try to see nonlinear correlations, for instance. I did this in the supplementary materials. I run other analysis to try to see nonlinear correlations, but I believe I can go further in this thing. I also run some analysis in grindability, but at the end, I didn't include in my thesis. I only got 4 clinkers of the 8, so it was quite hard to see correlations. But we got for the clinkers, we grinded in a mill that provide us the energy needed to grind each clinker, and we saw a good correlation, for instance, with the light. But as we only had 4 clinkers, I didn't include in my thesis. But I really believe that we need to focus on grindability, because as I see in the scientific community, some topics that are not given attention enough. And I think grindability is one of them, because if you make the clinker more reactive but harder to grind, you will grind less and will be less reactive. So I believe we have a lot of things to work on grindability, and I think I will continue on this path as well.
Yeah, and talking a little bit about the relations you got. We have, I'm not criticizing your work specifically, but it's more general comment. We have to be very careful, because it's very easy to use the computer to put correlations together, but we really have to understand if they make sense. Otherwise, we may spread some knowledge that is not really true, we are working with. So it's just a warning. It's very tempting, especially for you young guys. You are used to do that, but have to be careful to see if really correlates to what we know and what we see in practice.
Yes.
I know the time you had to prepare the PhD is limited, of course, but maybe if you are going to continue the work, some things you could focus to refine what you have done would be clinker microscopy, which I think is fundamental. Is really fundamental. I really believe that to see the clinker can give a lot of answers to the questions you still have. And another thing I missed sometimes was about the fineness of the cements you prepared. That could explain some things that you also you came like, you could not explain based on the results you had, but maybe analyzing the fineness would help. For example, in page 29, we have a discussion that maybe the fineness could help to explain. So I'm going through my notes here. And sometimes also I saw some kind of contradictions. For example, you talk about the role of the fluoride as a flux. And it's clear, it's very well explained. You decrease the viscosity of the liquid phase, and then the crystals of C3S are smaller. Perfect. And then you talk about phosphorus. That has the same effect. The viscosity, but
yeah,
opposite.
This was something that I wanted to change, because I discovered after the publication. He was talking with a person from the industry, because we have this problem that academic, we don't know how the industry operated. So what they said to me, when you add calcium fluoride as a mineralizer, you adjust the new to have the mineralizer. So you adjust the new rotation time, you adjust the length, flame length, and this kind of thing. So, and while phosphorus maybe is coming from the raw mill. So I believe that the effects on a light crystal size is, as you say, I saw correlations and I was, oh, very nice and put on. But a light crystal size is very dependent on the process parameters. So the time, the residence time of the melt in the new, the flame length, because the time that the melt is in the new is the time that you have to the light to increase, get larger. So what they said to me, I don't know if it's right, but it's from a cement industry, is that usually when you add a mineralizer, such as calcium fluoride, you usually change the new operation to have this mineralizer. So I believe this discussion is not right because I don't have the process parameters to discuss on. So I have uncontrolled factors affecting this beyond the chemical composition. And this is because the contradiction. For me was, I didn't have explanation because phosphor and titanium has a increase light crystals and fluor decreases. But perhaps it's because of these changes in the process.
Okay, okay. Another thing is that the role of the alkalis and sulfate is very known. And sometimes I kind of felt a little bit of confusion in the way we were talking. Sometimes we were talking about SO3, the total content of SO3, and sometimes the soluble sulfate that is combined with alkali. Maybe to make it more clear. And in talking about this, to me it was strange, and also in the presentation, I still did not understand the correlation between the optimum SO3 content and the SO3 in the clinker. I would not expect a correlation, maybe with the soluble sulfate, but not with the total sulfate.
Okay. Yeah, this was strange at first for me, but what is saying that if you have more sulfate in clinker, we obtain a higher sulfate demand. Because in the sulfate content, I am considering the sulfate in clinker and the sulfate as gypsum. So what is saying? If you have a clinker without sulfate, this will need less sulfate, total sulfate, than a clinker with high sulfate itself. This for me is like the sulfate in clinker is not as effective as the sulfate coming from the gypsum. So if you have a less sulfate in clinker, like for instance, let's take like a mix with 3%. If you a clinker that doesn't have sulfate, like the white one, all of the 3% is from gypsum, so it's soluble. And you got like PCE that has 1.7% of sulfate. So from this 3%, 1.7 is from clinker and 1.3 is from gypsum. So what is saying that is not all of this 3% in PCE is soluble. So I don't know if I, at least in the first 24 hours. Yeah.
Does not make too much sense, I would say, because you are assuming that the sulfate clinker is not soluble.
No, in this first part, I was assuming that all the sulfate was soluble. I was doing like the standard. I was considering the total sulfate in clinker and gypsum. So 3% is not 3% from gypsum. It's 3% from all the sulfates in clinker and gypsum. So in this first part, I was doing like the Brazilian standard, the STM, sorry, considering all the sulfates. So I was considering that all of the sulfates in clinker was soluble and reacting as the same as gypsum. That is the standard say. So in this case, it's not true. Yeah. So I discussed after about that because this STM standard doesn't separated the sulfate from clinker because it's hard in practice. Yeah, you have the clinker, you mix with with gypsum and you do XRF. So for the XRF, all of sulfates have the same. So the discussion that I'm bringing here is that we need to look careful for the sulfate in clinker, because not all of them will be ready and soluble in the first 12 hours to control aluminate reaction. I don't know.
Yeah. Okay.
Paulo wants to.
Back to this, and I'm studying how to go back so you can explain better. So soon you are going to visit us, so you can go in person.
Yes, that's
Silvia, may I do a proposal for José here? Perhaps we can also plot the calcium sulfate content, not just the total sulfate.
Yeah.
Perhaps it will be clear.
Yeah.
Right.
And in fact, plotting the calcium sulfate content, I already did this, but I didn't include, I will. All of the clinkers was about the same calcium sulfate content, except for the white one and the PCG. The rest, the 6 clinkers, was about 3 to 3.5% of optimum sulfate. Gypsum. 5% of gypsum. But I will do this, I think will be.
Okay, I have some notes here. I don't want to also to go into much detail because I will, afterwards I can give you comments by written so we can discuss, or I will go to more general issues. And for example, back to what I mentioned before, I need some discussions. For example, page 56 about the mineralizing and correlation. You said, well, the weak correlation may result from different factors affecting C2S and C3 contents. But I mean, which factors? I think it was missing to analyze it a little further.
Okay.
Something.
What I want to mean here is that all the cement plants will aim generally to obtain a certain level of allied content. So for instance, if you have a cement plant with the raw material with low reactive in forming less allied, you will include a mineralizer. So to form more allied. But if you have a cement plant that already forms this allied content, you will not include the mineralizer. So I believe is the analysis here has this problem, because if a cement plant has already reactive, you won't put the mineralizer. And if the other one has, you will put to try to read this level. So you can see the influence of mineralizing, because you are only using mineralizing when the allied content is low. Do you know? I don't know if I'm clear.
Yeah, actually, it's not really the case. We know that mineralizer does not change too much, at least the amount of daylight before. Why the system becomes more reactive? Because the daylight becomes much smaller. We have data, internal data, we can even share with you afterwards, showing a difference in clinker with and without fluoride. And the main difference is not the amount.
It is quite interesting because, as I said, the industry has a lot of knowledge that is not common for us, because we don't have a lot of mineralogical studies nowadays, but the ones that we have, they usually say that, oh, you add mineralizer to increase the allied content. And as you said, it's not the case. You are decreasing the crystal size. So it's very interesting. Thank you. I didn't know that. So I'm looking forward to see this data as well, because it's quite interesting.
The value of this work is tremendous. geology. It's really amazing because it's one of the few works we have of academic that is trying to see and to teach us about how we can improve our Clinker and our cement in the end. So all my comments here should not be seen as negative, but it's more, you know, I'm so happy with what has been produced. I read twice. And I will read more times because I want to get all the good information you provide, and I really would like to see more.
Yeah.
So I hope you will not abandon us. And we will ask you with whatever information you need from the real side, from the industry.
Thank you very much, Vivian.
Talking about this, again, we should explore a little more some correlations because when you talk about credibility again here, I mentioned the case of pela. Too. You mentioned about the magnesium that has a strong impact on credibility, but also has a strong impact on the light formation because it hinders a light formation.
Yes, it's correlated. And yes, exactly.
Yeah. So maybe to explore a little more evidence that will confirm things that we know by experience. The industry may not have a lot of theoretical knowledge, and unfortunately, we have been losing it throughout the years. But we have some practical. And then I think if we combine our knowledge with yours, we can do wonderful.
Yeah, for us, it's very important to have this industry perspective as well. Thank you very much.
Well, as I mentioned to you, I have a lot of small comments here. Maybe I can give you by written time. But to finish, I would like really to congratulate you and Anna and Paul for the wonderful work and also for the openness you have been showing to share with the industry. So good luck.
Thank you.
And wish you a lot of success in your future.
Thank you very much, Silvia. Thank you all for all the comments, the data, and everything. Thank you very much. It's very valuable for us to have these talks with the industry because, as you said, we as academics doesn't know the day to day in the fabric in the industry, and we need to know because we need to study things that will help you to progress. Yeah, we don't need to reinvent the wheel. So thank you very much.
And I told José that we don't allow him to leave, and we are kind of engine together, and with you all. This is why we are like trying to make things closer between industry and academy with the SPCC, the work group and TAC and all of that. So we hope we still working together. And thanks also for the Intercement for share all of this work because a lot of things we discuss we are very open about science.
Thank you so much, Silvia, for your point of view. And José told in the Cement conference that if industry don't come with the problems, the academia will have to invent some problems. So it's really great to work closely to the industry and see actual practical applications of the José's work, and I guess his PhD work complete both tasks, right, in the scientific innovation, but also in pointing, at least raising some questions or confirming some things that industry already know, but often the academy doesn't realize so clearly. So we are really glad to get this interaction with the industry. So following our guests here, I will pass the word for Professor Erich Rodrigues, originally from Colombia, but now from Santa Maria. Erich, thank you so much for taking the time to read the PhD document and the thesis document, and the time is yours.
Okay, Jose, thank you very much for your invitation. For me, it's a pleasure to be here, to be part of this time that very important time for you, that is going to convert as a doctor. Most of the questions was already commented by the others reviewers, but my comments will be related from a holistic or general point of view, okay? Because the quality of your work is very high, considering the articles already published, so, and even in the most recognized scientific journals. So, considering that we have a correlation between source material from the cement industry and all scientific measurements using different kind of techniques, which from your results, what would be your main recommendation for the industry, taking your data and the results?
So this is a very big
Which was
question. Who is me
your
to give
main
recommendation?
your main recommendation?
Okay.
Easier to be applied, cheaper to be applied for the cement industry, to be a higher or best clinker?
Okay, so this is a very big and difficult question, but I would say some things. First of all, Ruben comment on that, and I think the first part is about the testing that we are performing in the cement industry, because like we are still doing the soundness test from I don't know how many years, the VK tests, I don't know how many years. We are doing blame tests, I don't know how many years. We are using XRF to do bulk. So I think we need to got better testing, refine this testing to the industry to have more data. In terms of XRD, that was the second chapter, I believe that obviously the industry won't have access to a synchrotron facility or anything else, but I believe it's important when to get XRD when it's possible, to know the mineralogical of your clinker, mineralogy of your clinker, but not only apply like routine measurements like a robot, because like to the day-to-day measurements, okay, but as Ruben mentioned, if you change the fuel, you will change the mineralogy. If you impact this. So to have a specialist doing the XRD measure quantification and analysis is important as well. And in terms of chemical and mineralogy to enhance the active, maybe this to confirm some things before, like the polymorphism. I don't know if the M1 is indeed more reactive. And considering not only to optimize a light content, like, oh, I need a very high C3S, 80% clinker to have a good clinker, but to see other things like a light crystal size, a light defect, this kind of thing. and to consider not only the main for oxides, but as I says, magnesium, sulfate, and alkali was very important in all the papers in all the studies that I did. So magnesium, for instance, is somewhat treated as, okay, we cannot reach the maximum limit, but perhaps you can use the magnesium to increase the clinker C3S content, for instance. So perhaps to look again to these minor oxides, that could be a good option.
Okay, but for example, considering that the cement industry, when you produce clinker, you have, I don't know, thousands or maybe millions of variables to adjust. And you make a correlation between a very deeper characterization using XRD, Cyclone, and also you use statistic models. So how can you make a correlation between that? See, considering thousands of variables, very expensive measurements that you need a lot of time, a lot of equipment, and I don't know, professionals that do that with almost thousands of results. So how can you tell us about how, after your experience, how can we reduce and start with that?
Okay, so in fact, I believe that good ways to connect academic and industry, because here we have time to do this analysis and we want to do this analysis, but the problem is we don't have the data. So that because I'm so glad to have this opportunity, this partnership with industry, because we got a lot of good data and we could work on. But obviously, if my point of view, I would need more data. I would need information about the new operation, the raw mill fineness, and everything else to try to correlate better. So as you said, you have near 1 million variables, so it's quite hard to see the partner here. So I believe it's to have good data and to work on these statistical methods to try to see if there is correlations and exclusive causalities and this kind of thing.
Yeah. May I interrupt?
Paula wants to.
No, just again interrupting. We can try to isolate some parameters in laboratory experiments like lab synthesis, but it will never mimic the operation of a cement kiln. So from my point of view, I believe also from José, it will be more representative to get a good amount of data and reliable data and try to find correlations from that in actual cement industry operation rather than try to isolate the effect of one or other item. So the way going through the more data and trying to find correlations, it will be cheaper because the industry already collect the data, and I guess this is better or more representative than try to mimic it in the lab, right?
Because I would like, I like the comment of Silvia, the comment about standards. So how can we improve our standards, what use our standards, making this correlation, so statistical and infrastructure characteristics, because there are a lot of things. Maybe you already say that you discover a new paradigm about the result. You have new questions arise from the result. So how can we improve or how can we advance to make this technical control about the clinker?
Okay, this is important. I believe first we don't have all the answers yet.
Yes.
So I feel that reading and looking for papers that we had a good basis on 80s and 90s, but the last 20 years people forget about Clinker, I think. And there is a lot of work on alternative cement and SCMs that are very important as well. But I feel that we have a lot to explore on Clinker. And as Ruben and Silvia said about the magnesium, if it is like only the problem maybe is when it's a cluster, not the content and the real content, about also sulfates, because if the sulfate is inside the light, it will contribute to the layered trigite formation or not. I don't know. Perhaps only the soluble sulfates will be important for the durability issues. So I believe we need to advance in some things that we don't know yet to try to change the standards. And I believe that the standards, as all of areas, will move to a performance-based standard than oh, you need to have this composition. No, you need to have this and this and this properties. I believe that will move as in Colombia nowadays in a performance-based standards.
I don't have too much question because I'm going to send you the document with some comments with very little comments. But again, José, congratulations for your job. I know that you will have a great path from here in the future.
Thank you very much, Erich.
Thank you.
Thank you.
Okay, thank you so much, Erich, for your more philosophical questions. But it's the power of synthesis is perhaps the harder in the written document. So thank you again, Erich, for the time spent in revising the José's thesis document. And now I will pass the word for Suzuki, right? So thank you so much, Suzuki, for all the support through the 4 years of José's work and for providing the samples and funding the project. And of course, without InterCement, this PhD would not be possible. So it's we are very glad to have you here in this final moment of the José's trajectory. So thank you again, Suzuki, and the time is yours.
Okay, Paulo, thank you. Good morning. First of all, I would like to thank José and Professor Ana and Paulo for inviting me to be part of this defense. I would like to pleasure my colleagues on the committee, Erich, Ruben, Silvia, Ana, and I would like to send a very, very thanks to the people from all cement plants that work hard to collect clinker and to send to university. And a special thanks to Silvia, who generously shared with José lots of clinker results and make a valuable help to him to develop his thesis. Thank you for everyone. I agree with all of the comments that Silvia made, especially regarding the limitation of this work, because all the regressions, correlations was made with chemical, mineralogical, physical analysis, and we know that parameters from kiln, ball mill are very important and impact, of course, the clinker reactivity, clinker mineralogy, and cement properties. So I recommend that this limitation should be clear in each chapter, because of course it is very hard to collect all the data, even for us, for industry. It is very hard to collect and make own regression. So this limitation should be in the text clear. Because each king has your own history. So it is hard to explain in few words our difficulty to make our own correlations, but it is important to consider this limitation. Another thing that I would like to comment is related to chapter 3. Knowing that pellicles formation starts at around 2% of magnesium content, what do you think to adjust your populations involving magnesium, considering these limits?
Okay, I don't know if the standards of like 6.5%, considering that a part of the magnesium is incorporated in the clinker main phases or not. So I don't know, but I think, as Sylvia and Ruben said, we need to revisit this topic to see that makes sense to have a limitation or not, and if this limitation is correct or not. Because at the end, this 2% that is incorporated in a light, the light will not, as I believe, take part in the expansion or soundness of cement. I believe it's only the periclase, and maybe if you have clusters. So I believe we need to investigate more about that. I'm not sure yet. I don't have data here about that to say something about that, but I believe we need to progress on this topic.
I'm sorry, I should be more clear. I'm not regarding the limit of. I'm not. My concern is the possibility to review the regressions and the correlations.
Okay.
Separating the magnesium that we incorporate in the liquid phase against against the pellicle formation.
Okay. Okay. This is a very valid topic. I did that, and I didn't observe any difference. It's very important difference. So I removed, but I did that. I had this kind of data I can share with you. But at the end, like, because you have the 2%, but at the end, it's like a dilution effect, right? You add more magnesium, you will have less clinker phases, other clinker phases, because you form pellicles. But I did this. I take like magnesium, subtracting the pellicles, and then I had the magnesium that was incorporated, but I didn't see clear difference from the regression, so I decided to remove that from the paper. But perhaps I can add this as a supplementary material. That would be interesting.
Well, another question I have. Another question is related to again the greenability. It is for, as Sylvia said, it is very strange. There's some absence of correlation. So as I mentioned at the beginning, I believe it is important to clarify the limitation of some limitation. the study. I'm not diminishing the work. But it is necessary to clarify that.
No, yeah, I agree 100%.
Operational parameters we are not considering.
Yes, and about that, I also saw that in the chapter 5, when like I see no correlation between alumina content and sulfate optimization. I know that if you increase alumina content on clinker, you will increase the optimum sulfate content. But when I evaluated these 8 clinkers, wasn't the most important, because perhaps a clinker with high alumina content, this alumina is as C4AF or has less reactive than the other with less alumina. So I believe in the grindability was something like that as well. I know that a belite is harder to grind than a light, but you have other parameters like periclase and sulfur that is changing a light in periclase as well, that impacts more. And so I believe that has these limitations, as like you cannot see, I don't see like, oh, this doesn't have correlation. That meaning that if I have a cement and if I increase this parameter, won't affect, you know? It's just that in this data, I believe I should make this clear. I believe in this data wasn't more important than the other parameters. But obviously, if you have a cement, a clinker, and you have more belite, if you increase belite and decrease a light, it will be harder to grind. As the same for the sulfate. If you have a clinker and increase C3A, you probably will need more sulfate to be optimized.
Well, I would like congratulations for the job. It's a very challenging job because there are hundreds of thousands of millions of parameters that can influence clinical mineralogy reactivity. So I believe the job, it's not the end of the job. Maybe it is the start of a hard journey to help us to understand how chemical mineralogical parameters can influence clinker cement properties. And the cement industry has a challenging journey because we need to, how can I say, incorporate different kinds of materials like alternative fuels, supplementary cementitious materials that can increase the complexity of cement production. So congratulations, and hope we can continue this kind of job.
Okay, thank you very much, Suzuki, for your valuable comments, but also for the help in all these 4 years, as Paulo said. It's not easy to get the clinkers because we had to get the clinkers to grind here, so all the effort made by you and by the cement blends, also by the central lab in the Intercement. I accommodate them a lot, asking me for the results, and they were always helpful. So thank you very much, and thank you also for the idea, right? Because I did the master's in pure phase systems. Everything was beautiful, and then Suzuki always said, "No, we need to go to the real one because in the real one it doesn't work like that." So this kind of discussion made me to go to a more real system, and I see that is quite difficult to. And I observed several gaps that now we can pursue. So the idea is to continue. This, as you said, is only the beginning. We had some answers, very interesting, but I believe we have more questions than answers. And this is quite good because now we can continue trying to answer these questions. So thank you very much for all the help and valuable comments today and during this 4-year work. Thank you very much.
The more we study, the less we know. This is the true behind the academic. So thank you so much, Suzuki, for all your effort during this whole 9 year working with us. And so thank you so much for everything. As I told you on Monday, we build our reputation and our work to do all of this connection we had with you since 2016. So thank you so much. So now the last but not the least, Ana, thank you so much for your participation. Ana is not from our area. She works in LCA analysis and the building sustainability. So it's nice to have her view on that. Thank you so much for reading and all of the things.
Okay, thank you, Ana, Paulo, and José for the invitation. It's always a pleasure, especially when we have the discussions in the level that we're having today, and we see the enthusiasm of you three in this defense. So thanks for inviting me. Congratulations also for you three for the outstanding job you made so far. I believe José is a really motivated and also outstanding student from our program. So really, I admit this is not my area of expertise, but I recognize the importance of the cement performance and trying to improve the clinker quality into the building sustainability. So cement is also, and it popped up some questions myself that I believe we should also discuss further in future projects. So I believe my role here is to check whether José's thesis attends or not our program criteria, which for me it's really easy because he surely attends. But just for some curiosity for you that are participating on the evaluation, this type of thesis structure that is in articles, it's not mandatory in our program, and it's still a challenge for our students. So what we find here, what we defined here in our committee is that the student should have at least one published article inside the thesis, which he has, and at least 3 articles. So in general, we have 2 articles to discuss with the committee because he has some time to change these articles prior to submission. So I believe this is an excellent example because the type of discussion that was made here, for sure, now you have time to think about it and consider on the thesis. So, and also we can, as I noted, open some new research fields for your group because, because great ideas were discussed here. So the discussions I found really nice. And also congratulate you for the enthusiasm of answering them.
Thank you.
Regarding the presentation, I must mention that and congratulate you for the presentation because it was really didactic. I like it also on your work that you clearly indicate what can be explained and what cannot, because then you have future work, what cannot be explained. You're not hiding your results. This is good science practice, okay? I really like the statistics, the correlations that you have, and I found the importance of the industry taking place inside the thesis. So I was going to ask you what was your challenge, but now I found out that the challenge with the industry, it's the real world problem. And it reinforces the importance of your thesis and the importance of the type of program that you have, the scholarship that is the contribution to the industry. I have some doubts, but probably I have a question that is more like a curiosity, but I will ask you later. Maybe you will answer. I have noted also that you are already a teacher and you explained it really well, the whole thesis. I could understand the point you made, although it's not from my area. And I have assisted Anna and Erich classes more than 10 years ago. So you have explained it really well. My main regards are related to when you use co-processing, the reality, the context in other countries is that you have controlled emissions on the chimney, you know? So maybe this is something that we could move forward, because I don't know about if we have this type of regulations, you know, like besides the quality of the clinker, also the emissions, if they are expected to change. So if you may have more dioxins or something like that. So this is something that. And finally, I believe that's it. Really brief discussion. Do you have of this Snellings study that correlates the environmental part of the emissions with the quality of the clinker?
Okay, so Sylvia and Suzuki probably can answer better than me. I don't know if nowadays in Brazil we have a regulation on that, perhaps in the amount of sulfur that is volatilized, but there is a lot of discussion going on. I saw in a Congress that they were adding and developing admixture to put in the new to get, I don't know, I forgot if it's the phosphorus or other thing that could be harm for the environment. So they developed a mixture target these alternative fuels to decrease the emissions. So in Europe, I believe it's quite advanced on that, but in Brazil, I believe we need to progress yet. And it's very important, obviously, not forget the environment. So we are changing the fuel to decrease the environment impacts, but we cannot decrease CO2, but releasing other things that are harmful for the environment. So I don't know if we have yet, but I believe this must be in the discussion and not only the clinker quality, as you said.
Thank you for giving discussion of each and every point of your thesis. It eases a lot the understanding of the thing. And this is my main point. I believe you are really a major researcher. I believe you deserve the admiration. I believe your thesis is going to be a reference in the area. So please be careful with this final review. And congratulations for the great.
Thank you very much. Thank you.
Thank you so much, Anna, for your comments. For the next step, we are going to work together. Thank you so much. So now I want to give the word to my colleague, Paulo, because he was the one who was closer to José during these 4 years. So this is why I gave him the leading procedures, because he was very special for us during all of these 4 years, right? So I told in the beginning that José would be my gift for him. So I'm sure now he can talk about that.
Thank you so much, Anna and José, for the opportunity, of course, in this co-supervision, but most...
It's supervision, not co-supervision. It's only the word here inside the program.
I appreciate the opportunity of being part of this research from José, and we started to work together in 2019 or 2020, about 5 years ago, and exactly on José's master's work, and we never stopped working together since then. And I have the privilege of now have Jose as my personal close friend. So we have a really nice relationship. And in terms of academic evolution of the work, I guess I don't have to say anything else that the committee already said. And just to highlight that Jose is an amazing person and has a huge heart. And I used to say, if you don't like Jose, probably the problem is you, it's not him. So he's a great human being, and I don't know if I know someone that doesn't like Jose. So this is very important, at least for me, the human relations. It's not, you don't learn anywhere. So it's in sense, and that's it, I guess.
Thank you.
Thank you so much for the opportunity of our cooperation in the last 5 years. Thank you so much.
So thank you so much, Paulo, for everything. They work together very closely and very hard years. So, and also I want to thank you for everything we passed during these 7 years.
Yeah.
7 years, and I hope that you keep working with us. We have a lot of projects to run together, and I'm really glad of the person you became, like a scientist. You were a scientist before, but now you cement scientist. Very nice to have that, and thank you so much for your kindness, for your how can I say so you were a kind person, very gentle, and everyone just have a lot of everyone gain a lot of knowledge. You are a good teacher, a good professor. So everyone just are learning a lot. Also, I learned a lot with you. So thank you so much for all of the knowledge you share with us. And you are not my student, you are my colleague now. So thank you so much for being you and you are.
Thank you very much. Thank you.
So thanks. So now we are going to the last moment. So now I don't know if ele pode falar. So now we want to ask for everyone to leave the space a little bit. And we are stopping the transmission for a while. Como é que eu vou fazer? Para a gravação. Calma, como é que eu faço? Eu tenho que criar uma nova janela. Ou eu posso ficar...
Nossa, tá o pessoal da banca aqui, né? Me ajuda. Well, after a long debate in a secret section of the committee, the jury decided unanimously for the José's approval.
So let's take a picture of the committee. Quem que vai tirar foto? And then you guys you can leave. Okay, só tinha que ver da banca. Ok, assim se continuar.
Se fecha todas as câmeras da gente na. Isso, daí aparece.
Vai ter que juntar um pouquinho.
Ele é salvo.
Muita calma.
So, Ruben, Silvia, Suzuki. Eles estão escutando. So, Ruben, Silvia, Suzuki, thanks for your comments and everything. So you are free to leave now. We are still here eating and working and chatting and celebrating. Thank you so much.
Going to take part of the best.
If you want, we have some.
We just took the hard work.
So next time maybe you can come here. Okay.
Thank you. Thank you so much, Ruben, Suzuki, Silvia. Really appreciate your time and your effort. Thank you so much. Thank you.
Sai. É isso, né? Isso. Aí vamos tirar uma foto.
Legal, aqui.
Me dê como funciona.
Entendi.